Welcome to American Wood Council's live learning event. This webinar is being recorded. By continuing to stay on the webinar, you consent to being recorded. Please note today's session is registered with the American Institute of Architects for 1 LU HSW and the International Code Council for 0.1 credit. Credits will be automatically reported to the AIA for anyone who has provided their AIA member number at registration. Now, we would like to welcome you to our course, Introduction to ANSI, AWC FDS-2024. This presentation is worth 1 LU HSW with the AIA and 0.1 credits with the ICC. To receive credit for the course, you must attend this webinar for a minimum of 50 minutes. At the end of 50 minutes, you will see your certificate appear in your console. Your certificate will also be in your learner profile within 1 day on learn.awc.org. At the end of today's session, our presenter will have a live Q&A with the audience. Please input your questions into the Q&A panel throughout the session. And without further delay, I present to you our presenter, Brad Douglas, Vice President of Engineering with the American Wood Council.
Welcome to a webinar on the American Wood Council's 2024 Fire Design Specification for Wood Construction, designated ANSI/AWC FDS-2024. Please note that this webinar and associated slides should not be used as a substitute for competent engineering support and expertise. Additionally, the webinar is being recorded, and by remaining a participant, you automatically consent to such recordings. If you do not consent to being recorded, please disconnect from the session. AWC received ANSI approval of its 2024 Fire Design Specification for Wood Construction as an American National Standard on September 28, 2023. The standard, designated as FDS 2024, is primarily the 2022 version of the Fire Design Specification that has been revised to better coordinate with the Chapter 16 of the 2024 National Design Specification for Wood Construction. The FDS brings together provisions for fire design of wood members, assemblies, and connections to meet code requirements. This presentation will discuss the history of fire design provisions for wood construction, existing wood design provisions currently in building codes, wood design standards, and numerous design aids that have been incorporated into the standard, and adds additional calculation procedures to address the added fire resistance and thermal benefits of protection provided by wood cover, gypsum panel products, and insulation. The learning objectives for today's webinar are: discuss the history of fire design provisions for wood construction and fire research data for unprotected wood members, explore general information about the Fire Design Specification standard, including definitions and notations as well as general fire design requirements, examine the specifications listed in the FDS for ignition and flammability requirements for wood products, review calculation procedures used to address the added fire resistance and thermal benefits of protection provided by the use of additional wood cover, gypsum panel products, and insulation. Before I get into the discussion about the Fire Design Specification, I'd like to provide a bit of history on how we arrived at a point where the standard was developed. For decades, researchers worked on methods of predicting the fire resistance of wood products. Since there were no calculation procedures, the wood industry, along with other material groups, ran comparative tests of structural members and assemblies in order to provide some level of acceptance. Wood products were specifically targeted because they were combustible materials that, even though they had good structural fire performance, better than some materials, it still needed a benchmark level. A particular interest was heavy timber mill and warehouse buildings that were being retrofitted for new mercantile and multifamily occupancies. Designers were concerned about the fire performance of these buildings, even though there were literally hundreds of years of experience with their performance. In 1977, T.T. Lee, a researcher with the National Research Council of Canada, published a report outlining an empirical method for estimating the fire resistance time of large beams and columns. That method was adopted in the National Building Code of Canada shortly thereafter. In 1984, AWC's predecessor organization, the National Forest Products Association, was successful at introducing T.T. Lee's method into the U.S. Model Building Codes. Work continued on better ways to estimate fire resistance of wood construction. Several reports were issued by researchers at the Forest Products Laboratory and various universities studying wood engineering. In 1988, Dr. Edward King and Bob Glowinski with the National Forest Products Association published an article in the Forest Products Journal entitled "A Rationalized Model for Calculating the Fire Endurance of Wood Beams." While its ability to predict the performance of wood beams was mixed, it was the first attempt to develop a fully mechanics-based method that estimated the contribution of elevated temperature region ahead of the char front. Also in 1988, a breakthrough was realized in the prediction of wood charring. Dr. Robert White with the Forest Products Laboratory, U.S. Forest Service, released his thesis on charring rates of different wood species. It took several years for AWC engineers to fully grasp what Dr. White had discovered. The point at which wood burns fastest is just after ignition due to the presence of oxygen. As a char layer forms, available oxygen is reduced. Thereby, the wood continues to undergo pyrolysis, but at a decreasing rate. Dr. White provided various equations that he fit to the species-specific data he had tested. The best fit was a nonlinear char rate. AWC engineers discovered that all of the species had a similar nonlinear relationship. Even though there were small differences between species, it was found that a general equation using nonlinear relationship could be used for all species. Through the mid-1990s, AWC engineers worked on a new mechanics-based model combined with a general equation for charring based on Dr. White's work. With Dr. White's assistance, comparisons were made against full-scale test results of beams and columns. In 1999, AWC published the first version of Technical Report 10 entitled Calculating the Fire Resistance of Exposed Wood Members. This first version of TR10, as it is now known, primarily focused on comparing AWC's new mechanics-based nonlinear char model with T.T. Lee's empirical method. In every case, the TR10 model fit the test results better, and it allowed for the design of beams and columns using all of the structural design provisions from the NDS for small members up to members lasting up to 2 hours. And it also allowed for including various loading configurations, the effects of bracing, and beam column interactions. As I said before, it also allowed extension to 2-hour fire resistance, where the T.T. Lee model was limited to only 1 hour. The first version was also included structural design provisions for heavy timber decking. In 2002, the design provisions based on the mechanics-based nonlinear char model were adopted as a new chapter in the National Design Specification for wood construction. As part of the NDS, the new Chapter 16 provisions were immediately available to designers, but since it related to fire design rather than structural design, designers still confused about its applicability. In 2003, AWC was successful in introducing reference of NDS Chapter 16 into the International Building Code Chapter 7 on fire and smoke protection features for the fire design of structural wood members. For the first time, the new mechanics-based nonlinear char model was included in a code reference standard specifically referenced for fire design of wood members. Also in 2003, AWC released a new version of TR10, which included analysis of large tension members tested at the Forest Products Lab. Recognition of NDS Chapter 16 and TR10 started to increase. In fact, one of the first reported cases of its use in fire design was for a large timber roof truss assembly utilizing U.S. glulam in Taiwan. Work continued on TR10. In 2013, the mechanics-based nonlinear char model was used to predict results of unprotected floor joist assembly tests. As a result of the model's ability to predict the performance of full-scale wood frame joist floor tests, it has been used as a basis for membrane protection provisions for wood I-joists. The limitations of applying the model to only large cross-section wood members was removed from TR10 and the NDS Chapter 16 in 2013. In 2015, the model was used to accurately predict fire test results of exposed structural composite lumber, beams, and columns. Also introduced for the first time was a new model for exposed cross-laminated timber. The cross-laminated timber char model was the first deviation from the original nonlinear char model. While the CLT model uses the nonlinear char model, it resets as the char front reaches the glue line between each layer. In 2015, the NDS Chapter 16 provisions were expanded to cover structural composite lumber products that had been tested, i.e. laminated veneer lumber, LVL, parallel strand lumber, PSL, and laminated strand lumber, LSL. Also, new cross-laminated timber stepwise char model was introduced for CLT design. The next big step in fire design of wood members occurred between 2015 and 2018. All prior modeling had assumed that the fire resistance of wood members was inherent in the behavior of the wood. As work on the Tall Wood Building Initiative began, it became clear that added provisions for the contribution of protection needed to be addressed. As a result, AWC and industry engineers pored over test reports of wood structural members and assemblies protected with both additional wood cover, fire-rated gypsum panels, and insulation. Both protected large members, i.e. beams and columns, and wood assemblies, i.e. stud walls and floor assemblies, were analyzed. With development of these new protection options, AWC realized that the design provisions needed not be limited to structural fire resistance time, but rather could be expanded beyond those limitations to predict thermal separation and burn through, two additional requirements for assemblies in ASTM E119. That provide for fire separation between occupied areas. In 2018, a new version of TR10 was released with an expanded title and scope, calculating the fire resistance of wood members and assemblies, which included the design of protected wood members and assemblies. In 2020, another version of TR10 was released that added connection design examples using the provisions of TR10. Of specific interest was an example of how to design the protection required for connections of fire resistance rated wood members, which is a requirement for the new types 4A, B, and C construction. As the scope and demands on TR10 expanded, an issue arose, including all of the new non-structural design information into the NDS was out of scope. The NDS addresses structural design and wood members and connections. That scope was expanded to cover structural fire design of wood members and connections, with the inclusion of Chapter 16 in 2002, but adding all the information required for fire design of wood buildings was more than could be accomplished in a single chapter on structural fire design. Between 2018 and 2021, work began on a new AWC standard entitled Fire Design Specification for Wood Construction. Initially drafted by AWC and industry engineers, it was later extensively reviewed by AWC's Subcommittee on Fire Design with broad input from industry. In May 2021, the pre-standard version of the FDS was released for public review. While the new FDS was written as a standard, AWC chose to call it a pre-standard because it had not yet gone through AWC's ANSI-approved standards development procedures, which is used for all other AWC wood design standards. Shortly after the release of the 2021 Fire Design Specification pre-standard, AWC's Consensus Committee formed a new task committee to review the pre-standard. For approximately 14 months, the Fire Design Specification Task Committee reviewed every provision of the new standard. As a result of a number of meetings and hard work of the Task Committee on the revised version, the FDS was forwarded to the Wood Design Standards Committee for final balloting, which was approved in August of 2022 and approved as an ANSI American National Standard September 13, 2022. As updates to the 2024 NDS Chapter 16 were being balloted, there were several coordinating issues that needed to be addressed in the 2022 FDS, so a new version of the standard was developed. Here are some quick snapshots of some of the modeling results of exposed wood members used in the development of TR10. While these graphics are small, I think they demonstrate the fit observed with the new model, and the actual graphs can be seen in TR10. The diagonal line indicates where the model results equal the test results. Data points above the line are over-predicted and points below the line are under-predicted. This is a test of large wood beams. This is a test of wood columns. This is a test of SCL wood beams. This is CLT floor and walls. This is wood tension members. And this one is lumber floor joist assemblies. Here are some of the modeling results of protected wood members used in the development of TR10. Again, the diagonal line indicates where the modeling results equal the test results. Data points above the line are over-predicted and points below the line are under-predicted. Top left is gypsum wallboard protected stud walls. Below on the left is gypsum wallboard protected floor ceiling assemblies. The upper center burn through of rim boards. Lower is burn through of gypsum wallboard protected rim boards. Top right is gypsum wallboard protected SCL beams. And bottom right is gypsum wallboard protected CLT floor slabs. One more graphic to demonstrate how the new provisions in TR10 and the FDS are being used. These test results were used to determine the contribution of gypsum wallboard protection for tall mast timber, types 4A and B construction. In this test series, otherwise identical assemblies were tested with no protection, i.e. the control, 1 layer of 5/8 type X gypsum board, and 3 layers of 5/8 type X gypsum board. Each test was taken to either structural failure or a mid-span deflection of 12 inches, which corresponded to structural failure in the first unprotected test. As can be seen here, a single layer of 5/8 type X added 41 minutes and 3 layers of 5/8 type X added 127 minutes, which averages out to about 42 minutes per layer. Altogether, these tests confirmed that 40 minutes of protection time can be assigned to each layer of 5/8 type X gypsum board when it is used as a non-combustible protection on mass timber. Not coincidentally, it is also corroborates the 40-minute time assigned to 5/8 type X gypsum board in the Fire Design Specification provisions and in the AWC section 722.6 when it is used as a membrane in light frame wood assemblies. The 2022 Fire Design Specification for wood construction was completed in August of 2022 and was approved as an American National Standard in September 13, 2022. While design provisions for exposed wood members have been in the National Design Specification since 2002, the 2022 Fire Design Specification goes well beyond the NDS, covering such things as design of fire protection of wood members, design provisions for thermal separation and burn through, design of protection of connections, design for fire blocking, draft stopping, and much more. However, work to update the 2018 National Design Specification to the 2024 version was still underway. As part of that update process, it was acknowledged that coordinating changes needed to be made to the 2018 NDS Chapter 16 and the 2022 Fire Design Specification. For the most part, these changes were primarily to section numbers and other provisions in both standards. There were also changes to the scope in the NDS Chapter 16 and similarly the scope of the Fire Design Specification. There were also a couple of technical changes primarily to clarify the intent of the provisions in the 2022 Fire Design Specification. The 2024 Fire Design Specification for wood construction was completed in August 2023 and was approved as an American National Standard on September 28, 2023. As I proceed through this presentation, I will point out a couple of technical changes. Okay, so let's get into the Fire Design Specification for wood construction. Chapter 1 provides general information about the standard, provides definitions and notations as well as general fire design requirements. Section 1.2 terminology updates definitions of terms used in fire design specifically to address wood construction. Section 1.4 material standards provides identification of building material and product standards and special requirements for fire design. Section 1.5 heavy timber enhances descriptions of heavy timber elements that are currently in the building code and clarifies dimensional requirements for heavy timber framing, dimensional construction requirements for heavy timber roof decks and floor decks and walls, and it adds acceptable types of toppings for heavy timber floor decks. One of the specific additions is the allowance of concrete or gypsum concrete toppings as a heavy timber floor deck. Section 1.6, Material Combustibility, clarifies requirements for combustible and non-combustible materials. It brings forward a building code exception that allows certain composite products like gypsum panels to be considered non-combustible materials, even though they usually have a combustible facer on the product. The provisions also clarify that if a product is not considered non-combustible It is combustible and subject to the requirements in Chapter 2 of the Fire Design Specification. Section 1.7 of the Fire Design Specification provides design information of fire-resistant rated construction. This chapter was extensively revised between the FDS pre-standard and the 2022 Fire Design Standard. It clarifies requirements for fire-resistant rated wood members and assemblies, including 1. It adds clarifying requirements for continuity of fire resistance rating for assemblies, not continuity of the assembly itself, which was clarified in the 2024 AWC. It adds requirements for supporting fire-resistant rated assemblies, including special requirements for platform construction, which was also clarified in the 2024 AWC. It clarifies that where a wood column is in a wood frame wall assembly, protection provided by the wall assembly can be included as part of the structural fire resistance of the design of the portion of the column, and where the column is entirely within the fire resistant rated wall assembly, the column can be assumed to have the same fire resistance rating as the wood wall assembly. This is a slight difference in the wording between what is in the code now, because some people have interpreted the current code language to only allow the fire resistance rating if it's the same as the wall, where this provision would allow the contribution from the wall to be included as a portion of the column protection. It's a slight nuance there, but I think if you read it through and read the code provision, you'll see the difference. 4 adds requirements for fire-resistant rated design of multi-span beams. 5 clarifies that in certain loading conditions, protection provided by a sealing membrane that also protects a beam can be included in the structural fire resistance design of the beam. And where beams are entirely within a fire-resistant rated wood floor ceiling or roof ceiling assembly, the beams can be assumed to have the same fire resistance rating as a wood assembly. 6, it clarifies that in certain configurations, protection provided by a sealing membrane that also protects a truss can be included in the fire resistant rating design of the truss. 7, it clarifies that where a wood member is required to have a fire resistance rating, structural connections of that member shall be protected from fire exposure for the time corresponding to the fire resistance rating of the wood members, except where the member and connections are tested together as part of a fire resistant rated assembly. For example, a truss plate that's part of a truss assembly that's tested together. It also clarifies design requirements for intersections of fire resistant rated assemblies, including where an intersection must be detailed to prevent burn through, where intersections must be designed as a proprietary fire resistant joint system, and adds requirements for protection of edges of membranes used as part of the fire resistant rated assembly, including detailing requirements to prevent fire from circumventing the membrane protection and compromising the assembly, and prescriptive detailing requirements for gypsum panel, wall-to-wall ceiling, and wall-to-wall intersections. Chapter 2 of the Fire Design Specification specifies ignition and flammability requirements for wood products and provides reference test standards to be used to show compliance with these requirements. Section 2.2 clarifies requirements for ignition resistance of wood products used on exterior surfaces. Wood products are typically exempt from the current NFPA 268 test because ignition usually occurs at or above a heat flux of 12.5 kilowatts per meter squared for wood products. But wood products are prescriptively limited in their use as exterior coverings because they are defined as combustible. Section 2.3 clarifies requirements for flammability of wood products. Wood industry has conducted extensive E84 testing of lumber species and wood panel products. AWC's DCA1 contains a list of industry E84 flame spread and smoke development test results. The list of industry E84 flame spread and smoke development test results currently containing AWC's DCA1 have been incorporated into the Fire Design Specifications Supplement A. Section 2.4 clarifies requirements for vertical and lateral flame propagation of combustible exterior wall coverings. Reference to NFPA 285 is proven useful in showing the benefits of fire retardant treated wood as an exterior wall covering in certain applications where other wood products are not permitted. Section 2.5 clarifies the difference between three types of installations: fire stopping, fire blocking, and draft stopping. There are three types of proprietary fire stopping products, and the FDS clarifies where they are required in wood construction. Membrane penetration fire stop systems that penetrate just the membrane. Through penetration fire stop systems, the center figure where it penetrates a wall or a floor. And then fire resistant joint systems, the figure on the right, where you want to stop passage of fire from one occupant to another. For fire blocking, the FDS provides an expanded list of 9 materials deemed acceptable as fire blocking materials, including criterion for approval of alternate fire blocking materials. It also clarifies where fire blocking is required in wood construction. For draft stopping, the FDS provides a list of 6 materials deemed acceptable for draft stopping and clarified where draft stopping is required in wood construction. Chapter 3 establishes fire-resistant design provisions that apply to all wood structural members, assemblies, and connections that can be designed using the National Design Specification. For those of you who are familiar with the 2022 FDS, the format of this chapter has changed slightly to correspond with changes in the 2024 NDS Chapter 16. Section 3.1 provides general scoping applicability limits of the Chapter 3 provisions. It provides a reference to ASTM E119 or UL 263 to define the exposure used to meet the requirements of Chapter 3. It provides a list of requirements where the fire resistance rating is determined by testing or by calculation. And it provides a method for determining design loads when using a calculation method with either allowable stress design or strength design provisions. Inclusion of strength design for LRFD has long been requested in the NDS Chapter 16 provisions, but until this section was written, it wasn't possible to do that. It basically matches the provisions in Annex A of the E119 test method. Section 3.2 provides calculation procedures for determining char depth of solid wood and cross-laminated timber members, consistent with NDS Chapter 16 provisions. It implements procedures for determining and designing for char penetration at intersections of abutting edges and exposed wood members. It provides an enhanced method of designing of exposed lumber decking to allow use of char penetration concepts in lieu of prescriptive methods permitted in the NDS Chapter 16. It clarifies special provisions for structural glue laminated timber provisions that are in NDS Chapter 16. And in previous versions of the NDS and 2022 Fire Design Specifications, the provisions for calculating the char depth and the provisions for designing structural wood members using the effective char depth were combined. During balloting of the 2024 NDS, it was pointed out that these provisions needed to be further separated, especially in the Fire Design Specification, where the char depth is often used for determining protection for wood members, not just structural calculations. The provisions, while not changed, have been rearranged in the 2024 FDS and the 2024 NDS to clarify the intent. Also in the 2024 FDS, the provisions for char penetration have been reorganized and clarified, streamlining the design process. Section 3.3, Structural Fire Resistance of Exposed Wood Members, provides calculation procedures for determining structural fire resistance of exposed wood members consistent with NDS Chapter 16 provisions. It also provides equations for calculating the bearing area for fire design. For fire design of bearing perpendicular to grain, dimensions of the bearing area measured from each exposed edge of bearing interface were reduced by an effective area depth of 1.5 times the char, not the 1.2 times the char depth used for calculating effective areas for other wood members. This adjustment is in recognition of the strength and stiffness loss of wood perpendicular to grain when exposed to steaming, when moisture and temperature below the char temperature occur together. While this provision was in the 2022 FDS, it was combined with requirements for checking char penetration at bearing interfaces. So the two checks were combined into one, requiring the bearing area to be reduced by up to 2 times HR. Further analysis and discussions within the committee concluded these checks should not have been combined. They're two separate issues. So the 2024 FDS only checks the bearing area using 1.5 HR. Section 3.4 provides provisions for determining the protection time provided by wood cover, Type X gypsum panel products, and insulation. There are a number of equations here, and I'm not going to try to go through each one, but basically there's an equation for calculating the protection time for each of these systems, or for insulation. We basically cover two types of insulation, mineral wool and fiberglass bat. Some of this may be new to you, but in general it follows the same mechanics and thermal behavior as we use in the other provisions within the Fire Design Specification. Section 3.5 provides provisions for calculating the structural fire resistance time of protected wood members and assemblies. If you look at this slide, they're basically provisions for providing the protection time for multiple layers of wood cover, multiple layers of gypsum panel protection, and then for insulation. Also, it should be noted that these are not necessarily additive with the fire resistance of the wood. It basically delays the onset of charring on the protected face of the member. So depending on whether it's a protection on the face or protection of a whole assembly, you might get slightly different answers. Section 3.6 provides provisions for calculating thermal separation time provided by an assembly or wood layers, Type X gypsum panel products, and insulation. Again, it starts with the same times assigned to the wood cover, the gypsum panels, and the insulation. The big difference here is that the last layer providing the resistance is reduced because of the potential of oxygen on the backside of the product. So for wood cover, that means we only use 85% of the time assigned to the last layer, the layer closest to where we're looking at the thermal separation. For gypsum board, it's similar. The off-gassing of the steam or water in the gypsum, we take a somewhat conservative reduction of 0.5 times the time assigned to the gypsum board. And then for insulation, we just use the insulation, the time assigned for the insulation. Section 3.7 clarifies that burn-through detailing is only required where thermal separation is required, and it links to thermal separation time calculations. In this slide, you can see that in this particular figure here, we're looking at the thermal separation and burn through that occurs that's impacted by char penetration at an intersection. And those are spelled out in 3234, and then the protection is provided in 3612, and how you calculate that burn through time is in 37. For gypsum panels, it's similar, although with a conservative estimate of 0.5 of the protection time, that's actually at the low end of the finish rating of gypsum. So there isn't much shrinkage at that point. So we don't have the same issue as long as we're using a lesser protection time. So that's at 0.5 times the thermal protection time. Section 3.8 provides reference to industry-tested fire-resistant rated wood assemblies that are provided in Supplement B to the standard. The list of industry E119 fire-resistant tested results currently contained in AWC's DCA3 have been incorporated into the Fire Design Specifications Supplement B. Note that most of these assemblies are included currently in the IBC section 721. Section 3.9 provides an enhanced component additive method. The assigned times in this method are based on calculation methods in FDS Chapter 3 and verified by a comparison with full-scale test data. Here's a stud wall calculation example. These results have been corroborated with industry tests. In this example, you can see that doing the structural calculations, we only include the 5/8 Type X gypsum on the exposed side and the assigned value for a 2x4 stud wall protected with 3.5 inches of mineral wool insulation is 23 minutes for a total time of 63 minutes. On the thermal separation calculations, we have on the unexposed side, we use half of the 40 minutes, which is 20 minutes, 19 minutes for the mineral wool insulation, and 40 minutes for the protection from the exposed side gypsum. So we're a total of 79 minutes. And this is corroborated again with test results. I think this assembly actually achieved right around 63 minutes. Was never close on the thermal temperature rise, but did fail structurally. Here's a wood joist floor ceiling calculation example. On the structural side, we only account for the joist and the gypsum. The 2x10 joist protected with 1.5 inches of mineral wool insulation provides 27 minutes, and the 5/8 Type X gypsum panel on the exposed face is 40 minutes for a total of 67 minutes. On the thermal separation calculations, the wood structural panel gives us 14 minutes, but we can only use 85% of that because of the temperature rise. The insulation gives us 15 minutes, and the 5/8 Type X gypsum panel again gives us 40 minutes. So that's 67 minutes. However, note the point down here at the bottom. If you account for the gaps that can occur in that panel, you would estimate burn through would occur at the gaps between the single layer of floor covering at 62 minutes. So there would need to be some additional protection provided there to achieve 67 minutes. 62 minutes still passes the test, so you've probably seen this test result with no additional cover, but sometimes it works out better to put 2 layers there to make sure that the thermal separation isn't the failure mechanism, or burn through isn't the failure mechanism of that tested assembly. Here's a wood I-joist floor ceiling calculation example. The thing on I-joist, there's 2 structural calculations that you need to check. One is the structural flange, and the other is the structural web. In this particular assembly, we have a 1x4, it's basically 3/4 of an inch wood strip that holds the insulation up, but it also protects the bottom flange and the web. So we get, and these calculations have been pre-done for the user. So in this assembly, we got 26 minutes out of the flange. We got 40 minutes for the gypsum for a total of 66 minutes. For the structural web, we get 20 minutes because the web isn't really exposed for some time into the test. The 40 minutes is, again, for the gypsum, so we calculate 60 minutes. The thermal separation calculation, the same as the one we did previously. It's 15 minutes, 85% of 13 minutes for the 15-30 seconds wood structural panel, 15 minutes for the insulation, 1.5 insulation, and then 40 minutes for the gypsum for a total of 66 minutes. Again, the note at the bottom, you would calculate 61 minutes if you only had a single layer of plywood covering the top. I can tell you that this particular assembly went 65 minutes. So this estimate of the web protection is probably a little conservative, but generally you can see that the calculation methods attempt to give you a good but somewhat conservative estimate. Section 310 provides specific requirements for design of fire protection for connections. Here are 3 example connections of wood members that are required to have fire resistance rating. These examples were all designed using wood cover to protect the connections, but similar protection can be provided by gypsum panels, a combination of wood cover and gypsum panels, or some other proprietary configurations. All 3 of these examples are in Technical Report 10. I invite you to review those and see, but we basically deal with not just the char rate, but the char penetration between intersections. That's an important part of designing this protection. Some of the proprietary systems use friction fit, or they use intumescent caulks or intumescent tape to help seal these gaps, and so those would all be proprietary, but there are quite a few out there, and more every day for mass timber. So I invite you to look at that in some detail. One of the major issues when designing wood connection protection is detailing the wood members and protection to account for char penetration. Where the edges of wood elements abut, such as at the edge of a beam and column interface, the potential effects of char penetration should be evaluated. You look at this figure and you say, okay, well, everything's pretty covered up pretty tight. But char penetration, even if it's initially tight, char penetration can still be a concern. Let's talk about char penetration as it works for designing these connections. As wood chars, its volume decreases such that the thickness of the char layer is less than the char depth. This difference between the char depth and the thickness of the char layer is approximately 0.3 times the char depth at any given time. This contraction can result in the formation of a wedge-shaped gap which propagates along the interface between the two wood members. For relative tight-fitting intersections up to an 1/8 inch wide, the FDS provides assumptions of ignition that extends into these gaps for a distance that's approximately twice the char depth. As a result of additional wood cover or blocking is required to protect the area around the abutted edges. Fasteners used to attach protection are not required to be protected. This is, again, the example I showed a second ago. This is one of the examples covered in Technical Report 10. This diagram depicts the profile of the char front on a floor-to-wall ledger connection when the steel angle hardware is properly protected. The char depth is labeled as HR. The char thickness is the width of the gray area, and you can see that the char front has formed a wedge-shaped gap at the interface between the wall and the 2x protection members. But the protection has been designed to account for the char penetration at the interface between the CLT and the 2x protection members. Because of this, the char front does not quite penetrate all the way to the steel hardware, so it's an acceptable design. As the latest addition to AWC's family of wood design standards that have all been approved as American national standards, the broadest acceptance is being sought in the regulatory arena. It's our hope that today's session is a brief look at the new Fire Design Specification, and there'll be additional presentations on more detailed analysis using the Fire Design Specification in the future.